Hey, good afternoon. It is a lecture time, and today is a lecture number 7. And today we're gonna focusing on kind of like giving a summary about what is that we have learned so far. And to that end, we're gonna uh, look a little bit about how is it we can deal with the examples we look at the week ago, and how is that we can solve those examples using a MATLAB software. And this is, by the way, something that I did not practice prior to this lecture, so I hope that there's no technical difficulties to do that. And let's just see. I hope not, but we will see that momentarily. And well, I said last week that there's not going to be any new information this week, so it's all about summarizing what we have learned so far. That wasn't really true because, having a little bit of hard time to keep my promises, and this time too, there is actually a one new thing, which is a tiny new thing that I would like to teach you. So it's not going to be anything too significant, but a minor additional information that I would like to share with you. And that is related to this thing, this constraint stabilization. And once we're done with that, then it's all about summarizing everything. And then how is that I'm expecting you to prepare yourself to midterm exam. And how is a midterm exam? That's something we will discuss in details today. Okay, so let's get started by first summarizing what is that we discussed last week. So last week we concluded that virtual work done by external applied forces and the virtual work done by inertia forces cannot, in general case, to be set to be equal to 0. And why is that? That's simply due to the fact that if you do so, then this is how the equation look like. This is what you can end up, oh, excuse me, here, this is what you end up to have when you're setting the virtual work done by external applied force. This is this guy here multiplied by virtual displacement, and the virtual work done by inertia forces to be equal. So you can set those to be equal only if this virtual displacement here is kinematically admissible. This is something that we shortly will discuss after next week, after the break, after the midterm exam. And you can make this virtual displacement to be kinematically admissible if it's not a violating against the constraint. But how that is explained here is that we really don't care about the constraint. So we're just imposing the virtual displacement to all the generalized coordinates, knowing nothing about the constraints. And because we know nothing about the constraints, this equation cannot be set to be equal to 0. But we can force this equation to be equal to 0. And these forcing techniques, there are actually several forcing techniques. And we're gonna learn, or we learned last week that there is this method based on Lagrange multipliers that is called augmented formulation. This is where we adding constraint to this equation. So we adding constraint to this equation with help of Lagrange multipliers. Alternatively, we could set this virtual displacement, this guy here, which has become to be a bit messy, such the way that is kinematically admissible. Kinematically admissible, I will explain that after midterm exam, and then you can set this equation to be equal to 0. And I think that procedure, entire procedure, is then called something as a coordinate partitioning approach. I'm not sure how well and how much details I will go with this coordinate partitioning. Maybe it's going to be a short news flash to you. Maybe. I need to think about that. And I see that there is already some comments in the chat window. Uh, so help to last homework. So, well, we can do that too. So we can take a look like how is the last homework, which I think it is due this Sunday. I can explain a little bit about how is it you can solve that. Okay, so forcing this to be equal to 0. That's what gives you the equation of motion. So how is it you can do that? So you can add this constraint to your original equation with help of Lagrange multiplier. Remember last week we looked at this mathematics, basic mathematics, and we look at how is that you can do the, how is that you can find an extreme of a function subjective to constraint. And we realize that there is this mathematical optimization technique which is based on Lagrange multipliers. And it goes such the way that if gradient of your original function and the gradient of your constraint are parallel at the position where the constraints are fulfilled, that's your solution. And that's, and I'm sure when you hear me saying that, it feels like equal, like making no sense. But what it means for us, it means that the gradient that is computed here related to externally applied forces, this vector here, gradient, then that is this inertia forces can be said to be equal to 0 in when these constraints are multiplied by Lagrange multipliers. That is what this means for us. This is like interpreting that unclear sentence in a multi-body language. So that's what it is. Now, only thing that is missing here, and now you can set this to be equal to 0, finally. Only thing that is missing here is that at the point where the constraints are fulfilled. So this is our final set of equation, which is called set of differential algebraic equations, because differential equation and algebraic equation. We could solve this as it is, but it is often easier to convert that set of differential algebraic equation to be ordinary differential equation. And when you do that, or how you do that, first of all, you can do it by differentiating your constraints twice with respect to time. And when you do that, then this is how the final form of equation of motion appears. Here's it is. So this is it. So this is a final form of equation of motion. And today there's a challenge, by the way. And no, not the chin-up challenge today. That's going to be later in this class. But this time the challenge is that I'm making my best effort to explain you multibody system dynamics in 10 minutes. 10 minutes. So I'm summarizing how you end up to have this equation of motion in 10 minutes. And what are the significant aspects in multibody system dynamics and what are the less significant aspects. Okay, so that's a challenge. And let's see how well it works. So here's our final equation of motion. And listen to me what I'm saying here. In this final form of equation of motion, unknowns are said to be in this vector here. And unknowns are acceleration of generalized coordinates and Lagrange multipliers. So these both sets, so they're not two scalars, but the both sets are our unknowns. And how you solve that? Well, you solve it by substituting here the mass matrix of the entire system. This is going to be the Jacobian of the entire system. Here is external applied forces, quadratic velocity vector, if non-zero, and then something what you can get once you differentiate constraints twice with respect to time. All right, then what next? Well, then you're inverting that system matrix. You put that in the right-hand side of the equation. That's your expression of accelerations and Lagrange multipliers. And from acceleration, you integrate velocities. And from velocities, you integrate positions. And then you move forward in time. That's how the procedure, that's how you're solving the dynamics. That's how it works. And with that, so in that previous equation, I would like to ask you, in augmented formulation, the one that is based on Lagrange multipliers, unknowns are, and the options are here, acceleration of generalized coordinates, Lagrange multipliers, generalized forces, acceleration of generalized coordinates, and Lagrange multipliers, and only one is correct here. Only one is correct here. So go ahead. I can see that I only have or already have 10 answers. I'm looking at my circuitry window here. So already that much. So soon we're going to have a bit more. And today we're going to go back to my favorite topic, right after this challenge of explaining multibody system dynamics in 10 minutes. And the challenge is that we're going to discuss, or there's an in-class quiz that is related to rotational particles. And that's where I'm thinking that we're going to get this 100% success rate, I think. And the game is on. Yeah, the game is on. So I see. So you guys are saying has to be 100%. Yeah, I am thinking the same all the time. I'm thinking the same, but then I'm always like, now it's gonna happen. Now there's no way that it's gonna happen. There's nothing that stops us, and there's always something that stops us. And it's not me. I'm not voting here. Look at my hands. So it's not me that intentionally make this incorrect voting. Enter your incorrect answer to be more specific. Okay. Let me see how is the stream, how healthy is the stream today. What? What is this? It's a 52 views only. Okay, so if there is a one lecture that you definitely need to follow, that's lecture today. So those are those ones that are not able to see this streaming. Please make sure that you are checking the recording because your life will be very difficult next week when you are preparing yourself to written exam without seeing this lecture today. So it's going to be not impossible, but it's going to be challenging. Let's put it this way. Okay. We got to 54 answers. That may be the case today. I think that may be the case today because I only have that few views in my YouTube studio. I see that it's a 50. It's still showing the 52, but 52 and 4 likes. Oh, that's nice. How much money I can get from those thumbs up, these likes? Are they making any difference in terms of payment from YouTube? Maybe it's not making any difference. Okay, so 58, which is weird. So how is that we have that many? So maybe you guys are looking or watching this together. So going back to my OBS here, gonna put this to be visible. So let me see, there's some last minute guesses about the success rate. I'm not gonna vote by myself about the success rate today. So I'm just thinking that it's high. Thinking that it's high, but how high? You will see this right now. So 58 answers. The correct solution is D. And we got the success rate that is high, but it's not 100%. Guys, what is that I need to do to make this 100%? I running out of the ideas. I don't know what to happen. I don't know what to do here. But let me tell you this. Later today, I'm gonna ask, how is that you describe the rotational particle, and you don't. You don't describe that. This is gonna be the answering the one of the in-class quizzes today. Okay. So let me take this off. This one here, and let me take myself. Now I'm a bit confused. I have so many windows open. So let's go here. Okay. So the unknowns are this vector here. This vector, which is a acceleration of generalized coordinates and Lagrange multipliers. So what that means, if you have a pendulum here, how many unknowns you have in that case? Well, in that case, you have 3 generalized coordinates because, yes, everybody needs 3 generalized coordinates. That's going to be 3. And then how many constraints you have? That's going to be 2 because of the rebel joint here. So that's 2 constraints. So there's a total of 5 unknowns. 5. Meaning that this system matrix here is a 5 by 5. And I'm checking out. Oh yeah. So I went up with the likes. So seriously, is it making any difference in terms of like popularity or something? I guess not. How can I see the likes? I want to see, like, I think that might be my record. Have to be my record. Oh yeah, 21 likes. Nice. But let me tell you this. Likes doesn't help you. So it's not going to help you to pass the exam. So that's the bad news here. Right. So this is how you know how you compute the number of unknowns. Hope you got it. So you compute it in a way that you're adding number of generalized coordinates and number of constraint equations. That's how you know how many unknowns you have to deal with. Okay, so let's move on. So this was the first in-class quiz, and now let me move on in my studies and in my story. And the next one is this. Remember the last week we studied the two different mechanisms that I'm about to solve to you, to solve the responses to you. And I'm going to add these MATLAB files to Core's Moodle site as well, so you can play by yourself. So we look at the two different models. The one was this kind of crankshaft mechanism, missing piston, but other than that, this is a crankshaft mechanism. And I think that I asked this the last time for you too. So I'm asking how many unknowns we have in this case. How many unknowns? And another example we discussed, which I'm not asking here, was this kind of like simple pendulum where there was a beam-like body like this connected to ground in primitive joint here, another primitive joint here. Okay, so hold on. I'm still stuck to this. So here. So game is on. Next game is on. Oh yeah, so then there's a proposal that I should change the room name such that people are not watching the stream are not guessing. And when upgrading the Socrates results, that's an awesome question. I think that I promised to do that a while ago, a couple weeks back, and I didn't. All right, so I need to ask somebody in my team to help me I just need to extract all the results from Socrates and ask somebody to do it. And that will be available sometimes next week at latest. Okay, so back to this one. So in this example, the number of unknowns will be, in this example, comma, number of unknowns will be how much? Options are 1 as a, well, I'm not saying anything extra here. So 2, 6, 11. And again, you guys are getting started with the 100% success rate. And now when you do this, I'm going to start playing another thing to you. I'm going to play this MATLAB to you. So I have these models, the first and second example. Let me see. Oh, no, it's the problem is that I'm not visible here anymore. But I guess it is. Oh, let me just see. Okay. Oh yeah, because it's the screen displacement. Okay, so display capture. Okay, so here's a MATLAB file. So now I have here different mechanisms. So I have this, the one that is the symbol mechanism, and then let me see where this is. This is kind of missing here. Why is it? It's not in this file? Because I can see that this one is here, but I cannot run that one. And this is the one that I can run. Yep. Yeah, this is my Jacobian, everything that I described last time. It's just I converted that to be in a language of MATLAB, and that's when I'm gonna run it. And for some reason, this other, no, it's here. So this is the symbol mechanism. No, sorry, one more time. This is that symbol mechanism. It's maybe a little bit of small font, so you guys can see that so well, but I'm gonna offer this to you later. So these are the 3 generalized coordinates, and then I'm saying how is the initial position, and I'm explaining the model itself in a separate file, and then I'm running this simple example, and when I'm running this simple example, this is how it finally looked like. And what was this? Oh, I think that I run it the different incorrect file. So no, my God. So what is this? I said that I did not check this prior to this meeting, and that was a mistake because something is not cooperating with me today. Oh yeah, no, I think that this is this second mechanism that seems to be okay. So this is how it is running. Okay, so this is the second mechanism. You see, hopefully, no, it's not changing the picture. But that's why I'm solving this whole system using this procedure we learned last week. And then not just the displacement, but I can solve all the forces, all the acceleration, everything that I want. So this is it. So this is the big moment in your life. And another mechanism, what is going on here? Why it is not willing to solve it? There was something weird. Okay, not that. So I need to take it off. Sorry about the demo effect. And now I'm with you again. Okay, and one more window that I would like to put the visible to you is this one here, of course. I need to check like what is this thing, and I need to find it out another file that for sure will run properly. Okay, I have 62 answers, 62, which makes me feel worried. And the reason is that now there may be the cases that, like somebody already mentioned, that some of you are not watching the stream, but you're guessing the in-class quizzes. Maybe that's the case today too. So what is the correct number? Correct number is 11. And the success rate is disappointingly low. Disappointingly low. Because okay, let me take this off. Let me put it this invisible, and let me take myself back to here. Okay, this system here, we have two bodies here, two moving bodies. So that means that there's going to be 6 generalized coordinates. Then I have revolutes on here, revolutes on here. So that's going to be already 2 plus 2 constraints. And then one primitive on here, which is 1. So it's going to be 6 plus 5, that's 11. 11 is a correct number. So there's 11 unknowns in this particular case. Okay. So I don't know what to think about this, but honestly, I think that there's going to be this one great in-class quiz later today where I'm asking how is that you're describing the rotation of a particle. We don't describe it. So I don't know if that's a joke or something, but make sure that when I'm asking that you're saying that we don't describe the rotation of a particle. So so let me see your reactions to the success rate. Okay. Oh, I see. Yeah, so you get a lot of depth on effect as well. So sorry about that. I need to take myself back to this example and play it to you. But prior to that, one more thing. And one more thing is something that I need MATLAB to explain it to you. This is related to constraint stabilization. And in this MATLAB, I'm going to run this mechanism, crankshaft mechanism again, but I'm going to make a minor modification to my model. This again may be a little bit of too small font to you to see this clearly, but this is what I'm starting to run this integration procedure. And this is my integration, or kind of the accuracy, how accurately I wanted to do it. So I'm going to run the whole thing again, but this time using the significantly lower accuracy. Now let's see what happens when I'm reducing the accuracy here. And this one is the one that I wanted to run it here. So this is the visualization. Where is it? Is it now hidden? So, oh, there it is. Here it is. Oh, I need to run this one more time. Sorry about that. Here's the visualization. I'm going to make it a bit bigger so you can see it. And it behaves like this. You saw it? Okay. So it's kind of weird. So it seems that, sometimes the crankshaft mechanism can be behaving like an airplane. So it's not necessarily behaving like a crankshaft mechanism. So I guess that what we need to do here is that we need to trust that that's a real behavior because it's based on computer simulation, right? So that's how it have to behave. No, it's not never going to behave like that. So something went wrong. And what went wrong here? First of all, something that is very important you to understand that the computer simulation can be close to reality. It can be close to reality, but never ever trust that is always according to reality. It can be close to reality, but there is always a possibility that is not describing the reality because it's just, the model itself is not representing the reality or there is something wrong in the numerical procedure. This time, there is let me see. We got the wild crankshaft. Yeah, that could be the explanation. But why this happens here today? It happens because the way we introduce the equation of motion, we need to take ourselves back to the slides, and I need to explain it in using this slide here. Remember, this is what we did. This is what we did. So we started here in having the equation of motion in such a way that there was this differential equation and algebraic equation. And then we made this kind of unnatural movement, and when we differentiated the constraint twice with respect to time, and now that helps us to put this in this form of ordinary differential equation. And as a result of this, constraints are not fulfilled no longer in a position level, but acceleration level, because this is how we're imposing this constraint. So as an acceleration. Okay, so what happens in integration procedure is that you're integrating from acceleration, you're integrating velocity, and you're introducing a little bit of mistake when you do that. So you're never absolutely accurate when you do this integration, but you can introduce certain level of errors. How much error? That really depends on your settings, the ones we just changed. And then you're moving from velocity to position level, and again you're introducing another set of errors. And then you're going back in the next time, and you do this again, and you keep on accumulating the errors. When you're accumulating the errors, what happens at the end of the day is that the constraints are no longer fulfilled. So they are no longer fulfilled. And that's when the crankshaft mechanism started to fly around. So it's no longer fulfilling the constraints, but it's doing something weird, something that is unnatural. That's where it is coming from. So it's kind of correct to say that this is because the wild nature of the crankshaft, but you can also say that because of the way the constraints are imposed. They're imposed in acceleration level, whereas they're supposed to be imposed in position level. This can be fixed. There's an easy fix to take care of that. And the easy fix, and this is showing like mathematically what it means. So we are not, we kind of missing this constant, and we are doing these integration mistakes, and that's where that is coming from. So you can take a look at the details from the lecture note. But how is that we can, this keep on explaining the same thing here. So let me take myself a little bit lower here. So what I can do here to fix this problem is that I can have something that is artificially accounting this velocity and position level. And these ones that are artificially accounting the position and velocity level, these are called stabilization. And this is kind of like, the way to describe this behavior is that I have here a spring and a damper. Spring and a damper that takes you back to position where the constraints are fulfilled. So let me explain it in a way that you have a pendulum here, okay? And you integrate the pendulum in the first time step, and the pendulum end up to be here, which is clearly a violation of constraint. So what happens then is these two pulleys here, these guys comes in a play. One pulley is called as a spring, another pulley is called as a damper. So they will introduce a spring that takes, this pendulum back to original configuration. And then there's a damper that makes sure that when you do this motion, there's no vibration, but you just put it in the back, but you're not introducing any like a numerical vibration there. And that's called stabilization. And once you have the stabilization, then the wild behavior of the cantilever disappears, or crankshaft disappears. That's it. That's called stabilization. One more time. So everything started because the way we're introducing the constraint. So we're introducing the constraint in acceleration level. And when we're integrating from acceleration to velocity and position, we're making mistake here. And because we're making mistakes, which we are not correcting, constraints are no longer fulfilled. And this fulfillment can be accomplished by introducing additional components that are called spring and a damper. And that's the way to go. Okay, all right. So that's about it. Too bad that, I got the message that one of the students have to go because you're going to miss this big time. So it's going to be this 10 minutes challenge, explaining multi-body system dynamics in 10 minutes. And I think that's what we're going to do next. So, recap. So let's move on to summarizing everything. And I know you guys are busy, and I want to make your life as enjoyable as I can. So here's the list of subject matters that I'm expecting you to master. So take a look at this list of topics, and now each one of these topics are rated by stars. And if there's let's say if there's a 2 stars, 1 star, and you're busy, then skip that topic. Leave it with the less attention. But if there's a more than a 3 star, this is something that for high certainty, I don't know what percentage certainty, but the high certainty you can see that subject matter in your midterm exam. So I'm going to give you an example here. I'm going to jump to the first topic, and then I'm going to make that challenge explaining the multi-body system dynamics in 10 minutes. And let me see, here is the first one. So description of planar body, that's 5 stars. That means that for sure you need to know this. You need to know this. And you need to put a serious effort to learn it. And we're going to go details each one of these slides, so don't worry. This is just a highlight. Description of spatial body. This is no longer that important. So if you're busy, this is borderline case. So you maybe even skip this. Let me see. Velocity. Okay, 2 stars. So leave it. Leave it if you are busy and you really don't care about the high grading of this course. Don't do the velocity. Do something else. Do the ones that are rated by high number of stars. Okay? So that's how it goes. And then back to the challenge. Okay. Now, let me take a little bit of coffee and make myself ready to this 10 minutes challenge. Okay. So, then there's a question that will the midterm exam, is it going to be exactly same exam in both attempts? Because you have 2 attempts to do your exam. No, they're not same. So they are based on the lottery system. So we have a pretty significant size of question bank, and then we're using some kind of randomized system to select which question goes to you. Once you go to your exam once, we do the lottery. We're selecting randomly the questions to you, and you do go the next time. Then they are most probably different. If they're going to be same, definitely you need to do the lottery because statistically the chances are very thin, next to nothing, I would say. But it's still possible. Okay. Yeah. All right. So you guys are already discussing about that. Okay. Now time is up. I mean, time is on. Time is on for my 10 minutes challenge. So here's a 10 minutes challenge. Okay. Multi-body system is a system that, as the title implies, is a system that consists of multiple bodies. What we wanted to do in a multi-body system dynamics is that we wanted to describe particles that makes up a body with respect to global coordinate system. So that's something that is very much an essence of the multi-body system dynamics. Because the particles cannot move relatively with respect to each other, the easiest way to describe particles with respect to global coordinate system is to use a assistant coordinate system. An assistant coordinate system we're using here is called body reference coordinate system. Body reference coordinate system is attached to body. So body translate, the coordinates will do the same. And if the body rotates, the coordinates will follow that too. So it's attached to body. And now what we can do then is that we can take a look where the body origin is located at with respect to global coordinate system. And that's going to be the vector r that in a planar case consists of two components. And then we need to convert the representation from this coordinate system, this local coordinate system, to be representation in a global coordinate system. And the easiest way to make that happen is to use mapping that is called 2x2 rotation matrix. And that converts a vector that is originally described by this coordinate system to be described by this coordinate system. And these two components, translation and converting from one coordinate system to another coordinate system, that is our kinematics. That's all you need to know. In this kinematic representation, when you look at the variables, components that are changing when body is translating and orienting or changing its orientation, these variables are the ones that are associated to translation, this guy here, and the ones that is related to this mapping, orientation. Those are the variables that we're going to use over and over again to solve a configuration of not just the one body system, but all the bodies in a system. All right. So that's the first step. Then the second step is that multibody system dynamics, the inherent nature of the multibody system is that bodies are connected together via constraints, which are mathematical representation of joints. There could be different kind of joints. There could be a revolute joint that limits the motion possibilities between the neighboring bodies. Like these two bends could be connected together via revolute joint, and that makes it possible that they can only, that this point where the revolute joint is then located cannot be separated anymore. So that's the one explanation, one example about the constraint. But they could be primitive joint, they could be translational joint. There are several different possibilities what the joint could be. By the way, in the planar case, in two-dimensional case, the choices are that simple. So it's only revolute joint, translational joint, and primitive joint. Okay. Now these motion limitations, these ones that are called constraint, they're limiting the ways how these generalized coordinates can change their numerical values. And that's why the constraints are a function of these generalized coordinates. And possibly time. Maybe if there is something that is called driven constraint that is introducing pre-described motion. All right. Now in a kinematic analysis, the number of constraint equations is equal to the number of generalized coordinates. And that's all you need to do and all you need to know to solve the kinematic analysis. So it's every single information associated to kinematic analysis is hidden to your constraint equations. This is the technique that you need to, how you can solve it, the kinematic analysis, is that you're solving this set of nonlinear algebraic equations. And the easiest way to make it happen is that using iterative technique called Newton iteration or Newton-Raphson iteration. And this Newton-Raphson iteration tells you how you find the position that fulfills this constraint. Then you can also solve the velocity level analysis that you can get by differentiating that equation once with respect to time, and acceleration you can get by differentiating this twice with respect to time. And that's the kinematics. Then the next step is that you take forces into account. And now we have two different forces. And these two different forces are coming from this equation that I'm sure you have seen millions and millions of times. So we have external applied forces and inertia forces. And what we wanted to do here is that we wanted to convert the forces that are originally described by using global coordinates to be expressed by, yes, you're right, using generalized coordinates. And these having very different natures. These are not easy to understand the difference. I mean, that how you can do one to another. But we can make this happen. We can convert this one representation to be another representation with help of virtual displacement. In virtual displacement, we can introduce the delta R, and the delta R, because we know that the delta R, the one that is here, is a function of generalized coordinates. We can use the mathematics and we can express this such the way the delta R is equal to QR multiplied by vector that is a partial R partial Q. This vector here is the mapping that converts the representation from global to generalized coordinates. And once we do that, then the force is applying in a generalized coordinates, no longer in a global coordinates, but they are converted to be in a generalized coordinates. In externally applied force for this guy, this is how it reads. So we kind of looking converting that to applying in the R, X, this is an RY, and the angle theta. That's it. And then we redoing the whole thing by introducing or saying, now I need to find out my pointer here. So we're redoing the whole thing by accounting these inertial forces, which is messy, but that's okay because we're just repeating that mechanically. So this is how the inertia forces can be written in a delicate way. But this is, the same that mass multiplied by acceleration. But now I'm explaining that mass by using volume integral over the density. But don't get that confused here. All right. And again, I'm converting that force to be expressed by these coordinates. How? Well, same story. Again, I'm going to use a concept of virtual work. Virtual work gives me that mapping that I desperately need. And then I need to use here acceleration of this equation that I'm introduced in the very beginning. This one here. How you do that? You differentiate this equation twice with respect to time, and you're done. All right, you substitute everything to this equation, and then the generalized inertia forces consist of two parts. The one where there's a mass matrix multiplied by acceleration of generalized coordinates, and something that is called quadratic velocity vector. Quadratic velocity vector is equal to 0 if your body reference coordinate system is located in the center of the mass. All right, now we have generalized forces, and what we need to do then is the final step. We need to set them to be equal to 0. So what you can do then is that you can say that the virtual work done by external applied forces is equal than virtual work done by inertia forces in such the way that you are counting that the forces that are coming from the constraints. This was this mathematical optimization procedure, which you don't need to know in details, but you need to know this, that because of this mathematics, there's going to be one more component here, which is representing reaction forces due to the constraints. Because the constraints, they do introduce the reaction forces. Think about the pendulum here. You think about the pendulum here, the reaction forces that this body here experiences are these two force components here. These two force components are the ones that are described by this Lagrange multiplier. So the Lagrange multiplier is a reaction forces due to the constraint. And where they're applying in a system, that is the one that is told by or mentioned by Jacobian matrix. It tells the where they are located at. Magnitude, Lagrange multiplier. All right. So you get eventually this set of differential algebraic equation. You take your constraint, you differentiate that twice with respect to time. You're able to convert that to be a set of ordinary differential equation. Done. 9 minutes. 9 minutes. It wasn't 10 minutes, but it was a multibody system dynamics in 9 minutes. Nice. Ooh. Now I need to take a look. What are your comments? I need to relocate my window a little bit to see your comments a bit better. Okay, then there's a questions that are related to exam itself. Okay, so I already answered that. Second attempt, it's most likely your questions are different. And because this is a randomized, I mean, this kind of like arbitrary system we have, this, or the system that using this lottery-based technique to select which question goes to you. And exam is in modal, so you don't need to do any kind of registration. No need to do that. So only thing you need to do is that you need to set the time that it's good for you, and then you just log yourself to Moodle. And once you click I started, you cannot take it back. Then you will go, and that's going to be your attempt. So it's not possible. I mean, that you can go back if you're inventing a time machine, but other than that, you cannot. So once you click I get started, time will start running, and you cannot take it back. That's going to be your one attempt, and you have two attempts. Okay. So how is that we computing your final grading, or the one that matters? The highest will account. So if you first time will do your first attempt, you do 1 out of 5. That's okay, because if the second one is a 5 out of 5, the one that is accounted is a 5 out of 5. Okay. No, it's not always the last one, but the highest. Highest is the grading system. Okay, so you were impressed about this 9 minutes. I was too. Like, awesome. So multi-body system dynamics in 9 minutes. Level of difficulty is something that is okay this time. So, but and it's going to be all the time same, not regardless if you're going to do first or second attempt. So we are not going to make it any more difficult in 2 different attempts. So it's all based on the lottery. So that's is not changing. Your second attempt is no more difficult than the first attempt. But level of difficulty is something that we're going to discuss next. And that's when I'm going to start introducing these stars to you. This how important is that each one of the subject matters. Now, here's what I definitely recommend you to do. Make sure that you have some kind of a symbolic math tool ready to your use. And maybe you can already make it in your use such the way that you have templates ready for questions associated to set, say, Jacobian matrix. That it computes the Jacobian matrix automatically for you. So once you're telling what are the vector of unknowns and what is a vector of constraint equations, so the Jacobian matrix comes automatically. That's what I recommend, because as soon as you start to do that by using a pen and paper, there is this chance that you can make a mistake, and when you do the mistake, it's possible that you can scoring 0 points, and that's because of the stupid sign mistake or something. So make sure you have these templates ready. And other where you need these templates could be maybe force related to questions, and then make sure you understand the concept. Make sure you understand the concept. Make sure that, if I'm asking you, like, okay, how you describe the rotation of particle, then you have to be able to say, no, we don't do that. We don't describe the rotation of particle because the particle is assumed to be tiny, non-dimensional things, so we don't describe that. Or if I'm asking what it means, or what is a physical interpretation of Lagrange multipliers, need to be explaining that it's describing reaction forces with the constraints. Okay, now with that, let's take a look. So description of planar body. Definitely you need to know that. You need to know that. How it goes. It goes like I just explained in this 9-minute summary. So we're using 2 components to describe a particle in a planar space. So the first component is the translation from the origin of global coordinate system to origin of the body coordinate system. Second one is accounting the orientation of body reference coordinate system. And then we have this vector u bar, and the vector u bar is a vector that scans every single particle within the boundaries of the body. Okay. This mysterium, man, this mapping concept, that's 2 by 2 matrix, like this one here. And this is an orthogonal matrix, meaning that if you're forming a vector from this column and this column, these 2 vectors are perpendicular with respect to each other. So they're going to have a 90 degrees angle with respect to each other, like is the case in Cartesian coordinate system here too. That's they are perpendicular with respect to each other. And they are unit in length too, which is not the requirement of the orthogonality, but that's they are unit in the length too, like is the case of the coordinate axis as well. So this is a concept that you definitely need to know in details. This is okay to know. You know what it happens when you extended this concept to three-dimensional space. Uh, and then I see that, okay, there is a question which is, so keywords. So not necessarily keywords, but you need to understand the concept itself. And because you can use lecture notes with you, so of course, I'm not asking like something that you can copy paste from the lecture notes. I'm not going to ask something like that, but I'm asking concepts, how well you understand the concepts. So that's what the exam is about. But back to this extension from 2D to 3D. So in 3D, the dimensions, of course, are larger. So we are we're describing everything in a three-dimensional space where there's a three coordinate axis. And for that reason, the vector R is no longer a vector that consists of two components, but three components. This rotation matrix is a little bit of complicated in the case of spatial application, but we learned that the one way to describe it is based on Euler angles, which is system or procedure based on successive rotation. I know I never ever do this translation. What is something in Finnish, but this time I need to say it because it's important you to understand it. So successive means peräkkäiset kierrot, successive rotations. That's what it is, and that's the only time that I use in this translation. And then we have here again this vector U bar. All right, successive rotations. Here's a concept. So we learned that these successive rotations goes typically that's the way that the first rotation, which is amount of v, psi, v, v, takes your coordinate system like that. Second rotation, which is amount of theta, will take place around once rotated. Hear me. Once rotated coordinate axis x. And then you do one more rotation, which is again z-axis, and this is a v. All right, maybe it's not, but you see the notations here, so don't care about my pronunciation, which is probably incorrect. Now, this successive rotation, you can get it by multiplying these vectors, matrices, with describing each one of these rotations together, and that's your 3x3 rotation matrix. For sure, I'm not going to ask, okay, give me the rotation matrix based on Euler angles, because that would be stupid thing to do. You can copy paste this directly from lecture notes, so it makes no sense to do it. But I might ask the concept, related to concept somehow. That I could ask. And I have some practices here, so you can get an idea after I have covered all these subject matters. Velocity. So you take the previous equation, the one that was shown here, and you differentiated this once with respect to time, and this is what you're going to get. These R, S, U, S are nearly impossible to remember. Okay, that's okay. I'm not expecting you to memorize anything. So this is not about the memorizing stuff, not at all. Because if you need to take a look at the lecture note, so they are ready in the lecture note, so that's okay. But the concept again. But I need to show you an example so you can get the better idea. What are the things that I can ask? Okay. Here. Now this is a velocity. This is a translational velocity, and this is an angular velocity due to the rotation. Simple. You differentiate that one more time with respect to time, you get an acceleration. Not very important because look at the star rating, 2 star. Skip it if you are in a hurry. But if you want to score high, don't skip it. Okay. So now we have three components that are translational acceleration, normal acceleration component due to the rotation, and tangential acceleration component due to the rotation. Okay, that's it. Generalized coordinates, you definitely need to understand this concept. Generalized coordinates, first of all, everybody needs three generalized coordinates. Three generalized coordinates. Where these are coming from? They are coming from the variables of this equation. So you need to take a look. What are the variables in this equation? These are the variables. These are the components that describes the translation and the components that describe the rotation. That's it. That's your generalized coordinates. Not difficult at all. Okay. Then the next one is a constraint equations. And this is where you need to, I mean, maybe we're asking you to create the constraint equation for certain simple kind of joints, describing simple joints like revolute joint, primitive joint, could be the case. Even, which I don't remember if this is really a case, translational joint, but I would say um, leave the translational joint. Focus on other type of the joints. Okay. Now, another thing that is important, how is it you can compute the number of degrees of freedom? So that's going to be the number of generalized coordinates minus number of constraint equations. That's it. There are several different scenarios. There is a dynamic system. This is what you need to understand. Dynamic system, the equation of, the number of degrees of freedom is always more than a zero. So it's one or more. They could be equal to zero. I mean, number of degrees of freedom could be equal to zero. And then you have a kinematically driven system. So you don't solve the equation of motion, or you don't create the equation of motion and solve that, but instead you're creating constraint equations and using kinematic analysis to solve the response. This is very important to understand. What's the difference between kinematic and dynamic analysis? Kinematic analysis, the number of degrees of freedom is zero. And you can make them zero by introducing pre-described motion. Pre-described motion. Here it is again. Here's a pendulum. Pendulum has a 1 degree of freedom. Let's say this the 1 degree of freedom is this angle here, but it could be Rx and Ry too. And now you're saying that this angle here is no longer free to move, but it has to follow this equation, sine equal to sine time. That's pre-described motion. And then you can solve the response by using kinematic analysis, because the number of degrees of freedom will be, yes, equal to zero. And the system might have a less than a 0 degrees of freedom, and that's over-constrained system, unable to move. But don't mix that to redundant system. Redundant system is something that constraints are not independent. They are not independent, but they are constraining the same set of same way these generalized coordinates, and that's something that you want to avoid. Okay, next. Oh, look at that, Jacobian matrix. How many stars is this? This is 1,000,000 stars. What is it you should learn from that? You should learn that to make sure that you can compute the Jacobian matrix. Okay? This is where I recommend you to use this symbolic math tool and some kind of a template in your symbolic math tool, because as soon as if you open it in once you have the exam on, it's going to be too late to learn how you can compute the Jacobian. It's not going to work out. Okay, Jacobian, what are the components? What are the ingredients you need to make it possible? So you need to know the vector of constraint equation, and you need to know the vector of generalized coordinates. So if there's one body, it's just going to be 3 generalized coordinates. If there's going to be 2 bodies, there's going to be 6. And somebody did the math. So it's 12 stars. 12 stars. It's just something significant. I don't know. But if you're 12-star general, I guess that you're pretty high ranked, I guess. Okay. So the whole thing about the Jacobian matrix is using this partial operation. So it's a partial C, partial Q. So unbelievable amount of partial operation, but you just compute it mechanically. So that's what it is. Not too difficult. Then kinematic analysis. Kinematic analysis you can conduct when you have 0 degrees of freedom system. And you can conduct that in 3 different steps. Position level is this iterative process that I mentioned in my 9 minutes summary. You take your constraint equation, and then you're solving these generalized coordinates using iterative manner, where you're computing the Newton difference. The Newton difference is not the solution, but it's telling you how is it you can update your coordinates to find the solution. All right, so this is like a GPS system. So it's telling you the direction where to travel to find your final destination. Okay. So then once you're done with your position level, then you can move on velocity level. This is simple, so it's a matter of substitution. And as it is in acceleration too, but then there is this evil, nasty person in the middle, which is a little difficult to compute, but doable. Somewhat doable, I would say. Okay, then generalized forces. This is what we discussed or I explained in my 9 minute summary. So it gets started by, or it's something that is important here is that you need to understand the nature of virtual work and the virtual displacement. And don't think about it, the virtual work look like this and it's going to be this tiny and this direction. Don't do that because you will be confused. Think about it, that this is a tool that introduces you relation between generalized coordinates and global coordinates. That's the way to understand it. And it converts your forces to be expressed in terms of generalized coordinates. Why? Because generalized coordinates are the ones that are you need to know that where the body translation, where the body is translated and how is its orientation. That's what you need to know. Okay, so here's something that I saw in my previous slide or in my summary. When you're using the summary, then you have this vector of generalized external applied forces. That's it. Practice this too because this is medium importance. It's not ultra important, but it's okay to be aware of. Then a bit more important than that is this generalized inertia forces. This is a concept like I just explained in my summary. So you take your acceleration, you take this mapping, you're substituting that to this generalized inertia forces, and then you can express that eventually by mass multiplied by acceleration, and then quadratic velocity vector. That's it. Mass matrix, different components, yeah, would make sense to learn that too. Particularly, you need to understand that you have these 3 different components where this is a mass moment of inertia, and this is a mass of the body. Okay, and this is the one that is combining the translation and rotation. Test this as well. Make sure that you can compute it. Quadratic velocity vector, not particularly important because it's only 2 stars. So it's something that is non-zero if and only if your body coordinate system is not located in the center of the mass. But if it is, this is non-zero and you don't need to compute it. So then the final thing is this augmented formulation. Stabilization, by the way, could be there too. So augmented formulation is 5 stars. Important. Make sure you understand the concept of this Lagrange multiplier and make sure you know what that stands for. What is a physical interpretation of Lagrange multipliers? Reaction forces, that's right. Jacobian matrix telling where the reaction forces are applying in the system. And make sure you understand this converting differential algebraic equation to be ordinary differential equation. Here's information. Attempts allowed 2 times. Exam will be available from Monday at 0, well, it actually should be like 001. This is when you can make your first attempt. So it's right after midnight. A minute after midnight, you can make your first attempt. And it closes 1 week before the midnight. So you have exactly, 1 week minus 2 minutes time to make it happen. Time limit, 2 hours. Grading method, highest matters. So make sure you do the both attempts, but don't do it if you're scoring high in your first attempt. Then it makes no sense to do it second time. Here are the instructions. This is going to be available starting on Monday morning, early Monday morning, or right after midnight. So read these instructions, and if you have technical difficulties, something that is not going to work out for you, you could email or even call to me or Surat. But if it is just that I don't know how to answer this question, don't call and don't email. But if you have technical difficulties, something went seriously wrong, then it would make sense to do it. Okay. So are you ready to practice? These may be the questions that you can find when you're entering this exam room. So let's take a look. First one. If A is an orthogonal matrix, then that matrix multiplied by without that transpose of the matrix without transpose, another way around is identity matrix. However, it is not necessary that the vectors made from the columns of the matrix will be perpendicular with respect to each other. True or false? Yeah, we have. Yeah, now there is a question. Do we have sample question? This is an example to you. So let's see how well you do. So let's see if this will be a serious thing. So this is not an exam, but I lost it here. So this is in class quiz. So it's not as serious as do this in exam. But I'm asking this. So yeah, results are computed automatically after submission. Once you do the submission, you can see your scoring automatically right after that. So no need to wait until the end of the week or anything like that. You can see it automatically. Okay, but here, going back to this, it is not necessary that the vectors made from the columns of the matrix will be perpendicular with respect to each other. This is a little bit of unclear language, but basically, it's not necessary. And how is it? Remember this orthogonal matrix. This is all the matrices, but you can think about this in the case of this 2x2 rotation matrix to make it a bit more clear to you. And I got 33 answers this time. So let's wait that I can see how well you do it. So this could be serious. This kind of question could be in exam. And the second definitely good example, what is that you could possibly find in exam. Okay, 30, what happened? Now I only got 40. Okay, so the number is increasing. Let me put this visible. Yeah, about the wording. Wording is complicated here. Wording is complicated, but use a Google Translator. That's okay too. The success rate competition. Oh, I forgot to check about the success rate competition previous time. My mistake. Sorry about that. But now you guys are not even thinking that this is going to be 100% anymore. So you are losing your hope. I don't know how to take that because, this can-do attitude. We should have the can-do attitude, of course. Okay, now but I think it's fairly low numbers, but the realistic, like 74. Yeah, I think that's a realistic guess. 50 is like, okay, statistically it's going to be 50. Is it going to be really that low? We'll see that. We'll see it. Okay, how many? Okay, I got 61 answers. How many it was last time? I don't remember that anymore. I think it was 60 something. So I guess that we are about to close this case. I'm moving on to next. Next one is my favorite. No, it's not yet my favorite. No, it's my favorite. It's definitely my favorite. Yeah, so if you're gonna use a translator, how it goes, I don't know. I don't know. Okay, so I got 64 answers. I think that I'm gonna close this case. So here it is, true or false? False. And this is a bit, I admit that this is not so simple because, not necessary. It is necessary. If you have the perpendicular condition is a must have. Otherwise, it's not going to fly. Okay. It's okay. If you're going to be this good in an exam, this will be awesome. But then my favorite. Here's my favorite. This is where I can be seriously disappointed. Seriously disappointed. Or super happy making my winning dance and winning song as well. Oh, God damn it. I forgot this multibody song. I need to. Okay. Come back after midterm exam and I'm going to play the multibody song to you right after midterm exam. All right. Yeah, I'm sorry. My memory is good, but it's just very short. So next one. Okay, so the game is on. And how you can describe a particle rotation? Particle rotation. You don't describe the particle rotation as it makes no sense. Or with help of rotation matrix, or with help of vector r, or with help of generalized coordinates. So how you do it? Now this is, I have to admit that the last one was a bit misleading because you need to read carefully. You need to read the text carefully. Okay, you guys are saying that today is a day, 100% day. Oh yeah, I'm getting scared because I have not made my winning dance ready. I have no multi-body song to deliver to you. So let's see how well we do. Many of you are voting this time, 100%. Okay, is it 100%? We'll see that in a second. Well, not in a second. We're missing couple students. I have 50, 60 answers at the moment. Okay, so yeah. So I would be, honestly, I would be a little bit disappointed by myself if it's not going to be 100%. And here is our Socrates. We got 66 answers, I say 67, so I think we're good to go. So, ready. Honestly, I'm a bit scared by myself to take a look. What is this? So let's just make it happen. Let's just jump to the water and let's see what it is. Ooh, closest ever. Never been this close. Never ever been this close. But not 100%. I don't know how to take it. I'm still happy. I'm kind of, honestly, I'm a little bit relieved because I wasn't sure how to make this a winning dance. I'm not really a great dancer, so that would be a fun thing to you guys to see, but no, you don't see it. And the singing would be equally inconvenient to me. So this is it. So that's it. So we don't do the rotation of particle because we don't do it. It's like a Santa Claus. It's non-existing. So it's an urban myth. So, but this is an example what you could possibly find in midterm exam. One more example. This one here. I'm gonna take myself to now. No, 3 screens. Oh, I lost. Where's my point? There's my pointer. Okay. Physical interpretation of Lagrange multipliers. Force is due to the inertia. I know there's so many. Yeah, you guys are computing like who made it? Who made it? Who's guilty in this action? Yeah, I can see that when I look at these class quizzes later, but I'm not going to release that information to you guys for sure not. But next one is on. Okay, next one is this. Physical interpretation of Lagrange multipliers. Force is due to the inertia. acceleration of generalized coordinates, rotation of a particle. Okay, no comments, even though that there's a high temptation to say something in that regard. Reaction force is due to the constraints. Now somebody is like, yeah, of course it's Santa Claus. I take it back. You know what I mentioned about the Santa Claus. I take it back. Okay. So here are the four choices. Which one is correct? Which one is correct? And we are collecting answers already. So I have 22, 23. So the number is growing. Is this going to be 100%? No, I don't think so. I don't think by myself. But the game is on again. Game is on. Who was, by the way, it was, what was the final? I think it was 98. We got 98 here. We got winners. Nice. Oh, now you guys are, you seriously? Do you think that it's going to be that low? Like 68? That's super low. I'm guessing 90. 9 is the first number, but what is the second number? That I don't know. Well, 90. It could be exactly 90. That sounds like a good guess to me. So still, let me put this on. So I got 53 answers. Now I need to take myself back here. This is where it's gonna go. And where's that I can find this multibody song? Is it in my mobile phone? I need to take a look at that. While you guys are looking this, I'm gonna check if I can play you a multibody song. It'd have to be like 20. Yeah, I think that I might have it in my mobile phone. Hold on. Getting closer. Yep, getting really close. No, yeah, I don't think that I can find it with this short notice, but it's not far. Okay, it's gonna be next time then. Next time I'm gonna play multibody. So there, I think there it is. Hold on. Okay, not today. Next time. But back to in-class quizzes. So we have 63 answers. And the success rate is this. Where is it? No, there. 70. I think it wasn't even first guess that was 70. No, it came later. It came later. So it's yep. No, there's no 70 here. Why not? Okay. Anyways. No, I was thinking that there was 70, but I don't see it anymore. Okay. Reaction force is due to the constraints. That's what these Lagrange multipliers are standing for. So they are not acceleration of generalized coordinates. These are the good examples you can find in exam. Very good example. Oh yeah, so it was there was a 70. There was a 70. Okay. 3 examples. What are the kind of material that what kind of level of difficulty you can expect to see when you're entering the midterm exam. So it's going to be this kind of questions where I'm asking something. You need to select the proper choice out of the many, or there could be a mathematical question. With that, I have no further things to say today, so I'm gonna close this streaming. Make sure you're watching this streaming number of times. Make sure you're watching that 9-minute summary several times, because what I mentioned in that 9-minute summary, every single statement you need to be able to understand what that means. Okay, what it means. And to be able to make yourself ready to answer this type of the questions when you get into midterm exam. And again, 2 attempts, highest will be accounted, and 3 hours each. 3 hours each. So make sure you have some level of privacy. And like I mentioned, so we take this plagiarism seriously. We will ask some of you. Again, it's going to be based on the triggers we introduce in a model system. We introduce some of you to oral exam, and we'll see how it goes then. All right, so then what I will do is that I'm going to close early today. So we still kind of 10 minutes to go, but I'm going to close today. And I'm going to see you guys in a team session in 2 minutes. All right. So have fun next week, and see you not next week, Wednesday. And by the way, I'm not sure how is what time is the lectures next period. This is something that I need to figure out. I need to send you an email through the model system. Anyways, see you guys soon in a Teams, and then you can we can discuss more details concerning the midterm exam. See ya.